Today's topic is the alternate light source. And the main point of alternate light sources is to change the situation in terms of contrast. So when you're looking at looking for evidence, or you're trying to take a photograph of evidence, you almost always need some sort of enhancement or contrast. You need good lighting and sometimes visible light, just because you are using your eyes to look around, may not be the best source of illumination. And so this whole talk is about alternate sources of illumination. We have all kinds of analytical methods that we've talked about before, the wet chemistry methods for large samples and so on, extraction of the analyte. We have different color analyses. So the chemistry of color, remember we did that lab in PChem1 with the RGB values. Before we got to the RGB values, we had the tri-stimulus values, the X, Y, Z, capital X, capital Y, capital Z. Well, those are based on that, the Commission on Color came up with those standard X, Y, Z values, and then there are other color schemes. We focused on RGB because we could type that into a computer and display it on the monitor. But there's CMYK, you've heard of that perhaps. That's for printing. So there's the different pigments that you print with, cyan, magenta, yellow, and then K is for black. And so you have those four pigments that can make a wide gamut of colors. And then you have the Munsell color catalog, you have the Pantone colors. There's a lot of different color systems, and sometimes changing color filters will enhance contrast. And then sometimes going to a different spectral region, like FTIR, is necessary. And if you can image in the FTIR, which we can upstairs in my lab, that's even better. It's very time consuming because you have to take a pixel at a time. And so you have to run through and take a spectrum in a grid and then look at that. That's called hyperspectral imaging. So you've taken an image and every pixel is a spectrum. And so then you can go through and take slices of that spectrum and look at it in terms of its coordinates. So if you want to think about a fingerprint, there's going to be protein in that fingerprint, and proteins have carbonyls. So if we imaged and took a spectrum at every pixel, we could then pick the carbonyl band, 1600 wave numbers, and we would image where the protein is. And we would see that fingerprint. It would show up. So that's hyperspectral imaging. The hyper meaning you've got spectra at every pixel. So it's just very data intensive. But now they're making infrared multi-array detectors. So you can just take a single shot. Basically, you're doing 64 by 64 spectra at the same time. So you put your sample in there and you can image a grid that's 64 by 64. Not great high resolution, but it may be enough for the analysis that you want to do. And then we have ASTM standard. If you can get a piece of the ink or a chip of the paint, you can analyze those different pigments. And we have this flow chart. So this is an ASTM flow chart. I know it's kind of difficult for you to see, but up at the top we have the physical examination, and then you start breaking the examination into different samples. So you can take if it's a paint, you can take the layers apart, like a vehicle paint, and you can look at the binders. So you can look for the polymers using FTIR or fluorescence microscopy or mass spec. You can take the pigments, and we'll talk about that in a second, and then the different additives like plasticizers. Maybe there's metal in there, so some of the automobile paints have metal chips or metal flake to give it a sparkle. That's evidence. So this is a really useful flow chart to talk about the different analyses that you have. For the metals, you're not going to use FTIR, you're going to use X-ray diffraction, X-ray fluorescence, or scanning electron microscopy. You're going to want something that deals with ideally the 1s electrons in those metals. Because if you can get an X-ray signal out of that metal and tell you where the 1s orbital is, then that tells you how many protons are in that nucleus, and that tells you what the metal is. So if you can get a handle on the 1s electron orbital energy using X-rays, then you know what element it is. taking the pigments and colors, you can do imaging, but right here we have alternate light sources. Looking at the dyes and pigments, and also for locating things that are difficult to see. Then we have imaging, like UV-Vis, FTIR, and Raman. And so this is the microspectroscopy, spectroscopy through the microscope. So it's not useful for everything, but it's useful for particular situations. If you're doing metals, you're not going to worry about the FTIR or Raman because they're not going to interact very well, very particularly. But you'll use X-rays for metals. And then you use IR, Raman, visible light for organic compounds. And so here's an example of the use of an alternate light source. Up above, we've got some piece of evidence that's been obliterated by a Sharpie marker. And all you have to do is change the frequency of light. And unless that marker was exactly the same ink as this ballpoint pen, you can separate the two. And so somebody took a ballpoint pen, message and eradicated it or obliterated it with a Sharpie marker and thought they were good. When you shine a near-infrared light on it, you have a near-infrared detector or imaging element, and you see right through the Sharpie marker.
So it's always best to shred your bills versus this.
Exactly that. And also, if you're going to mark through something, mark through with exactly the same ink that you used to write it. It may not be an option, but we got this note from someone else. Can you send me the pen that you used? I want to mark through this. So that's, and plus criminals aren't necessarily thinking that way. A lot of times you'll find that our ability to catch somebody is because they're not the brightest person, And so a lot of our safety depends upon the stupidity of criminals. So these are various alternate light source setups. This guy's using a green laser light. He's got the power supply here. So this is the power supply. It's got a long fiber optic cable and a shining laser light, and he's dusting for prints on this bottle. And notice he's wearing orange glasses. And so we'll show you what's going on there. This is another laser power supply. It looks like it's in the blue. And then I've got one of these. It's not a laser, but these LEDs are getting brighter and brighter. And so I bought this $35 at Amazon. And so these crown lights used to be over $100 each. And so it does put out 365 millimeter lights, which is in UV. So if someone don't want to take turns, you can come up here and look. We can see how dirty my keyboard is. Okay. So and the plastic is enough to block the UV. Okay. Well, if you have glasses, that'll block the UV. All we need we need some sort of plastic or glass between us and the UV. And so if you look at this silver, yeah, y'all not come up here. Let me do this. Let me switch. I'm going to go to 5 here. Okay. I'll shut this down. Okay, so if you're not up here, you can see up there maybe. And so your skin has got all kinds of bodily fluids in it that don't evaporate. The oils, fats, the proteins, and everything. And a lot of the proteins have amino acids that have those fused rings. And those are the fluorescent compounds. So those fused rings in the protein are fantastic fluorophores. So you can see particles right there. And so there's evidence. There's a pink fluorescent particle there that I could pick out with some tweezers. And so if somebody wanted to know who was using this laptop the most, my DNA is all over this thing. It sounds gross, but that's the evidence here. and so we can. Now it would be hard to pick out someone else's DNA because mine's all over it. So if somebody used my laptop once and you tried to sample it, you would probably not find their needle in my haystack, right? But you can find stuff all over the place. Now, if you had taken, let's say I was, Could you see? I wasn't looking at the screen. Could you see it on the screen at all? No, too bad. Let me try to take the camera off just camera may not even be, yeah, optically sensitive enough. Can someone turn up the lights for me? Oh, there we go. All right, so we can, yeah, so you can see all that stuff. Okay, my inner key is pretty bad. Look at that key. Yeah, so I'm trying to get it to where it doesn't. And so I can put an orange filter on this camera, and or one that's more blocking most of the UV and just giving you a little bit of a blue, then I would definitely see it. Look at that little orange particle. I just can't really see it. If I had an orange filter, that particle would stand out like crazy. I can see it with my eye, but the camera that I'm using is not the best. Okay, so that's using an alternate light source to find evidence. And you can use it to image, so they have fluorescent fingerprint dust, and we use that in the quality cleaning workshop to teach people how to clean desktops and countertops, and good wiping technique. And so you just dust a little bit of that powder down, you can track it with the fluorescent light or UV light, and then you wipe the surface and you can see how clean you have it. Okay. If you have fingerprint oil on a surface, you can dust it, and then that fluorescent powder sticks to the oil and gives you good contrast for the fingerprint. Then you shine one of these lights on it and take your photography. You develop the photograph and then look at the ridge patterns to make a match. Okay. Or an exclusion. So that's the point of this alternate light source. It's trying to find evidence and better characterize evidence. There are a lot of different kinds of light sources. This one is, I think it's pretty good, but they make better ones. They make brighter ones. They make ones that you can shine, like stand stationary and shine on the carpet and on the walls. It's so bright that you can see the fluorescence from feet away instead of inches away. And so some of these are on here, like this mercury vapor lamp, the tungsten lamp, white LED. It's a barcode scanner here, so it's nearly 650 range in terms of nanometers, and then bright sunlight up here. So it's just showing you the illumination profiles. So there's different types of light sources. You really, if you want to get the fluorescence, UV is good. You really need the UV. So a quartz halogen lamp gives off mostly visible light. And so if you get a lot of UV, you'll get a lot of fluorescence. Metal halides, again, they give you sharp peaks in the visible region. And if you have a filter, like you're trying to filter out the blue light so that you can see the fluorescent light, and you're putting a lot of energy into that filter, trying to block that light, then your light heats up. And xenon has a good UV and a flat response in the visible, but it gives off a lot more heat than light. So managing heat is probably the biggest problem with some of these light sources. That's why LEDs are so transformative, because this light, most of that light that's coming out, in the LED, is coming out in terms of the visible light or the UV light, not in heat. Whereas these other incandescent lights, or maybe even gas discharge lights, there's a lot of heat involved. In fact, all of the incandescent lights, all it means is you're heating up a wire. And heating up that wire, you're getting its black body radiation up into the visible range. What is to get to thousands of degrees to get it that hot? It's a tiny little wire at 1,000 degrees. It's going to generate a fair amount of heat that you need to get rid of. Whereas the LED, they're up to 20% efficient. 20% of the energy you put in, it comes out in terms of light. But an incandescent, it's about 4%. So you put in 100 joules and you get 4 joules of light out. Whereas the LED, you put in 100 joules, you get 20 or 25 joules of light. And so this is a xenon arc lamp spectrum. And you can see the visible range, about 15% in the visible, 35% in the UV, and 35% in the visible, and then 50% is infrared. And this is maybe on a few occasions might be useful, for most of the time it's just blown away with a fan. So you're just taking that heat away. These are different companies that sell these fluorescent light sources, but I should also add Amazon on there. Because everything can go through Amazon now. So that's been really helpful for me. Okay. And so these light sources allow us to find and visualize more evidence. I know it's kind of gross, but I mean, you can look on here and see on my handkerchief which place I use, and you can get my DNA that way too. And so here's a pretty busy fabric pattern. You use that light on there, and you can find stuff. And it's kind of gross, but if it's evidence, right? You know, you got to get over your grossness if you're collecting the evidence, especially in some of the crimes. To work efficiently, we need to know how they work. And so let's understand light, and let's understand filters. Let's understand fluorescence and detectors. And so let's look at these different tools. You know, these lights are used in all these different kinds of analyses, even shoe prints and biological fluids. This is probably the number one, is finding biological fluids. In fact, that's the selling point on the Amazon page. You know why they sell this? It's not for crime labs. Anybody know?
Cat urine.
Exactly, cat urine. Yeah. What's more common? You know, some drug-facilitated sexual assault or a cat peeing on the carpet. Right? And you want to clean that, spot clean that to get rid of the odors, because most of the odor is ammonia. So as the urine decomposes, it produces ammonia, and your house starts to smell funky. And so you want to find it, and you want to spritz it with some OxyClean or some Febreze or something that's going to oxidize that urea and get rid of the ammonia smell. And so you can just walk around with this, and you'll find a bright spot on your carpet, and you go, ah. or they spray, like male cats, if they have been neutered, they'll spray on the curtains, and that smells. And so you can find that with this light, because those compounds, those especially the proteins in those sprays will definitely fluoresce. Yes. Okay, please. Oh. Yes, absolutely. You can see the bitterness in their face. Did it again, sneaker. We're going to fix this, and we did. Yeah, he never forgave me, I don't think. So, yeah, the look on his face when I went to pick him up was like, yes. Yeah, so luminol is an interesting compound. So in the presence of iron, so it's looking for blood. So if you have a luminol solution, this is a molecule that's been activated by hydrogen peroxide, and so it's in an excited state. And if it comes into contact with, I don't know if it's a reducing or oxidizing reaction. I have to go back and look at the actual chemical reaction. But if it comes in contact with the metal that will activate it, like iron, then it will chemiluminesce. So it's a chemical reaction with iron that emits light. It's very cool. So you can spray this luminol on a spot that you suspect might have blood on it, and get your camera ready, which now with video, you would be videoing this. You would spray the luminol on there, and the chemiluminescent reaction would show where there's blood. And it's very, very sensitive, because anytime you detect light, like we saw, we couldn't see it invisible. I mean, with the room lights on, we turn the room lights off. Now we've got a very dim background, and the fluorescent bits of skin and sweat were emitting light. They were absorbing the UV and emitting visibly. And so we had a low or dark background, turn the lights out, and then that's a really important point. Fluorescence and chemiluminescence are the most sensitive techniques you can have, because you can turn down the background, and then the evidence emits light. So that's the best situation ever. So luminol will react with blood, the iron in blood, and give off light. And so you would use that as well. That would be not necessarily an alternate light source, because you're not hitting it with a source of light, but an alternate chemical that emits light. So in terms of absorption, we would use powders, like dark powders on fingerprint oil, to try to absorb the light. And so in absorption mode, you're looking at contrast based upon absorbed light. And then we could enhance, like if you have a red background, then you would want to enhance it with a different color light. So maybe you change the light source to enhance the difference with the background. And then fluorescence mode. So this Northmen 6G is an orange powder. It's super bright. It's maybe one of the components in like Jared's shirt. It's that color orange. It's kind of a coral or bright orange. So this is one where you've got visible illumination. You can shine a red light on those and the red goes away. And anything that's not red, it's visible. And so here, you can't see what's written under there, but it's there. And if you shine it in the red, then the red fades into the background, so everything is red. And your eye naturally picks out whatever's not red. And so you can see all of this different writing behind the different paints by changing the color of the visible light. Here in UV, this is a receipt of whatever has been marked through, and you can see through the markings. This one I love. This is using infrared light on thermal paper, okay? And you can see how some of the numbers have been erased. So they used an eraser, and what does your eraser do? It might remove the graphite, but it leaves behind a lot of natural rubber. And that natural rubber from the eraser is embedded in the paper, and you can shine in the infrared where natural rubber absorbs, and take a photograph. This is a negative, and you can see where the natural rubber was. And you can add up these. That looks like a 1. These look like maybe a couple of 1s, and so on. So why would somebody want to erase numbers? Well, they may come up with a tally that's short. 1, 2, 3, looks like $3,000. And so they come up with a tally that's $3,000 short. That $3,000 goes in their pocket and make a deposit that's $3,000 less that matches the tally sheet. And so it's as if that money never existed. And so they've got the deposit account sheet here. They erase the numbers. They put that money in their pocket, and then they go deposit the numbers. And so this would be evidence to show that this had been tampered with. We can use a color wheel for contrast as well. So you use the opposite color to eliminate a particular color. So blues would eliminate reds, and red filters would enhance the reds. And you can use the different fluorescence light sources. So if you hit it with a blue light and it fluoresces, all of the fluorescence has got to be red shifted. And that was one of the questions on CHEM 1. Because if you think about fluorescence, you have, say, a UV absorption, and then the molecule does something in the excited state to relax a little bit, and then you have emission. Okay, so it's absorbed this amount of light, it relaxes a little bit, and now the gap is smaller. And so it's red shifted. It's a smaller arrow, therefore it's a longer wavelength of light. So all you need to do is to have the illumination be blocked by your detector. So we don't see the blue light. So a lot of this depends upon the filters. And it filters on your camera and it filters on your eyes. Now the glasses we were wearing were not filter glasses. They're clear. But you can buy orange or blue blocking glasses, and so you wouldn't see that light at all. And you'd just be shining it around, and the only thing you would see would be the fluorescent light coming through. That's the most sensitive. These are different kinds of filters. You've got barrier filters that let certain amounts of light through and block others. And so in this case, you've got a filter, it's a notch filter that lets the excitement light through. So this would be a filter on your source, and that's what's going on here. This filter tries to block all of the visible light and only let the UV through, so that only UV light comes out here, and then you don't have the visible light to confuse your detection. So that would be the exciter filter. That would be a bandpass filter. We'll discuss what bandpass means here in a second. And then this is a low pass or long pass filter that lets the fluorescent light through. And so this is the optical system. And this is what we were doing here without filters on my desktop. We were shining the light on the desktop, which had a filter that allowed only the light we wanted to illuminate with. And in this case, it was UV. Here in this screen, it's blue. So this filter is letting blue light from the source hit the sample, and then the blue light is scattered. So there's a lot of blue light coming off, and then sees everything orange, yellow, and red. It sees all the long wavelength stuff. That's the fluorescent light. And it doesn't see the source. Because you can turn the camera sensitivity way up if it's not looking at the source. Okay, if you let the source light through, the camera's going to be blinded. It's going to look into a bright blue spot, and maybe there's some orange photons of light in there. But if you block off the source light, so see here, it's being blocked, then the camera can be set at its most sensitive setting, and it can see the most dim amounts of fluorescence. And so that's how we isolate that fluorescence light. We use an emission filter to select the illumination wavelengths. So these are all vocabulary words: illumination wavelength, emission filter, and then the detection filter that blocks those illumination wavelengths. And that's being shown right here. So 1 is the emission filter, the 2 is the detection filter. And only those fluorescent wavelengths are detected, which means that we can really crank up the sensitivity on our camera. I should bring my camera in. You can see it's got an ISO setting, which is sort of the sensitivity on the detector, that goes from 100. Mine goes up to 128. Let's see. Yeah. 64. 12,800. I think it's 12,800. So that's quite a bit more sensitive than just a 100 ISO. The different types of filters, we have the interference filters and absorption filters. Interference filters are kind of exotic. They're really only used for laser light sources. And all the others are absorption type filters. But let's talk about the different types. Okay, the interference filters are much more expensive. But if you're buying a laser illuminator, they're probably going to come with an interference filter. The cost will be put in with that laser. They tolerate a lot more heat than absorption filters, so they're the best in terms of their ability to run for long periods of time, but they're tied to a particular laser and they're more expensive. So here's how an interference filter works. It has a very specific thickness, and that may not be the thickness of the whole filter, but there may be a layer embedded inside the glass that has this thickness. And that thickness is a multiple of the wavelength of light. And so that's why it's tied to a laser. A laser has a single wavelength of light, or close to it. And so this interference filter is tuned to that wavelength of light. Let's say it's a 532 nanometer laser like we have upstairs for the Raman system. And so that interference filter is some wavelength that is a multiple plus a half of wavelength. So 532, that's nanometers. It's hard to make a 532 nanometer film. But you could make a 1064 nanometer film. So 1064 is 2 wavelengths. So in that case, n would equal 2. But we need it to be 1/2 a wavelength larger. And so can someone divide 532 in half for me? 532 divided in half. 266? Is that right? I think so. Okay, yeah. I think you're right. What is it? Okay, 266. And so then you would add 266, that's half of the 532 wavelength, add that to the 1064, and that would be the ideal, and one of the ideal thicknesses for that layer. And that's about a micron. So we can make a micron layer very accurately. So we could just deposit this plastic or metal on a glass surface and then put another glass surface on top, and we have an interference filter that's going to block 532 nanometer light. Now, how does it block the light? Let's follow the path. So this wavelength of light comes into the filter, and so follow the blue, right? So the blue is the initial wave. It goes into this layer, and it hits here, and it gets reflected. So now it's red. It goes backwards. Okay? And notice how it's a full 1 wavelength and a half. So it gets here and gets reflected again. Now it's green. Notice the green one is the exact opposite phase of the blue one. And so it's green here. And when it reaches this point and comes out the other side, this reflected wave that's been reflected twice inside much of the initial wave. So this cancellation produces an exiting wave that's transmitted that's much, much smaller. It doesn't ever cancel it perfectly because internal reflection isn't perfect. But it cancels a lot of it. So you've got an incoming intensity, this blue, really, really bright, and an outgoing intensity that's really, really small. And so these can knock down that wavelength easily 1,000 times. So 0.1% of the light's getting through, which is great, and maybe even more than that. Knock it down even more. Now, would you put this on the source? No, because you'd be killing your source. So you shine the source on the sample, you would put this interference filter on the detector so that the source light hits that detector on your camera or on your eyes, and none of the light gets through, or 1 out of 1,000 photons gets through. Now, where does this energy go? Well, the thing about the interference filter is it's angle dependent. And so what this really does is it steers the transmitted beam off axis. So there will be angles through here at which there's constructive interference, and the beam actually gets brighter. Isn't that weird? Okay? So you would have angles where the beam is bright and angles where the beam is really, really dim. And so we want the normal, the straight path through to be the dimmest. And then if some energy is coming off at other angles, it'd really be a cone. If you've got a laser coming in, it'll be a cone, and there'll be a bright ring, and that bright ring has all the energy that's missing. So this filter doesn't absorb energy, is my point. The filter redirects the energy to other angles. It's a monochromator is what it is. So you could take a slice down this way and you would see like the dispersion pattern in a monochromator, a diffraction pattern. And so as long as you stay on the normal of that glass filter, you're going to have a very dim amount of light coming through. If you get off axis, it works against you and you get very bright light coming through. But the main point is, how do we keep this filter from heating up? We use an interference pattern like this, then the filter doesn't heat up very much at all. Absorptive filters absorb that energy, and so they heat up because they're just gobbling up those photons. And so this is an absorption filter. You have Beer's law operating inside the filter. And if you want a darker filter, you put in more pigment. Just this is the path length, you have the absorptivity, and you have the concentration. So the darker the filter, the higher the concentration of particles that are absorbing that light. A lot of times you just have like these neutral density filters that just have carbon in them. And that carbon absorbs all the different wavelengths of light fairly equally, but they heat up. If you wanted to get a particular color, then you would dope this with some sort of organic molecule or metal complex that absorbs those colors. And so where did this energy go? It goes into the molecules that are in the filter. So this energy, if you put a lot of energy in, the filter heats up. So you need fans. You need to cool those things with convective airflow. And so these are some photographs from the text. And this, I want to explain what's going on. You'll get this if you buy a filter set, it'll probably have pages and pages of spectra of your filters. And this is the kind of thing that you're going to see in the little manual that came with your filter set. And I want you to be able to read it and know what kind of filter this is. So this is a transmission spectrum. Always begin with the axes. So you have transmission on the left, you see 0 to 100%. And then across the bottom we have wavelength. And a lot of times they'll have it listed as an edge wavelength. And that edge wavelength is defined at 50% transmittance. And then you got to see what's being plotted. See this black curve? This black curve is the curve for that filter. So if you stuck this filter in a spectrometer, that's what you would see. You'd see a high part where it transmits the light, and then it drops down to 0 where it blocks the light. And this filter is called a high-pass filter. So why would that be a high-pass filter? Look at the spectrum and explain to me why it's a high-pass filter. What's the word high mean in this context? High energy. High energy. or frequency. Energy and frequency are proportional. So we've got Planck's law up here. And then what's new? Very good. HC over lambda. So lambda is inversely proportional to energy. Frequency is directly proportional to energy. So a high pass filter passes high energy, passes high frequency, short wavelengths. So the short wavelengths, that's high energy. So this equation is your friend. This is how you decipher all of these things. This one is a low pass filter. You see why? What? Low energy, exactly. It's also called a long pass filter because of long wavelengths. So anytime you see short or long, it's talking about wavelength. And so this one here is a short pass filter. A high pass filter and a short pass filter are the same thing. Short wavelength is high energy. Short wavelength is high frequency. And the EW, the edge wavelength, is going to be where that cutoff is, at the 50%. And we picked that 50% wavelength because, this slope here, depending upon the thing that's absorbing, that slope may not be as steep as you'd like. And so you've got to find some, make a call. How are you going to label this filter? Well, you pick the 50% mark. So no matter how shallow that line is, it's going to cross 50% someplace, and then you report the wavelength for that. So let's say you inherited a filter box of filters from some other forensic lab, and they don't have this documentation. Okay, what are you going to do? Are you going to go get your visible spectrometer, or are you going to scan your own filters? And then you're going to put some, tape on the side or in the box where you have them stored, and you're going to label them with the edge wavelength. So you just go in and pick the 50% mark on the absorption line or transmission line, and you've got to do it in transmission because it's 50% transmission. So you do a transmittance measurement, and you pick that 50% mark, and that's the edge wavelength. So here's the edge wavelength for the transmission of a long pass or low pass filter. Notice the 50% mark doesn't tell you which side is transmitted. So you could have an edge wavelength, this is 550. So an edge wavelength of 550 doesn't tell you what kind of filter it is. That tells you what a cutoff is. If it's a high pass filter, then wavelengths that are shorter than 550 will be transmitted. If it's a low pass filter, then wavelengths that are longer than 550 will be transmitted. And so this is something that I will definitely test you on so that you get all that straight. Here's the edge wavelength and its low pass. Here's the edge wavelength and its high pass. What actually comes through that filter? And then this is a bandpass filter. It's actually two filters put on top of each other. And so for a bandpass, you have two 50% transmission marks. And you reject things that are higher in frequency and things that are lower in frequency. And then you have a maximum transmission in the middle. And so here we label the central wavelength of the bandpass filter. And so sometimes this might just be labeled like this one would be a 460, say, a 460 bandpass filter. So you know that the center wavelength is 460 nanometers. You really ought to know what the width is, and so you might have to look that up. If you don't have it, you have to scan that filter. You know where the central wavelength is, 460, but it doesn't tell you how wide the band is. And so you've got to actually look that up. It may be labeled 460, and it tells you where the center wavelength is, but again, you won't know how wide that transmission line is. And so this would be something that, again, this would be in the blue region, 400 to 550, so blue-green, and that would be great for a lot of organic molecules. So this, you put this one on the source, and only this light would come through and hit the source, and then fluorescence would occur over here. And so then you would put a long pass filter on your camera and wear some some glasses that have a long pass filtration on them, and you would see all the fluorescent light that's going to be emitted in this dark region. So sometimes you have two filters. You have the illumination filter and you have the detection filter. Here's the xenon scope, and you can see the light source is down here. The light comes out this lens area. You've got some slots for filters, and you can rotate this thing through and put different filters in. So the filters are built into this light source. It's a this xenon halogen lamp is very similar to a car headlight. So you see how bright those are. And so it's got a fan and a power supply in the back to keep that thing cool. But it gives off, a wide spectrum of light, and so that you can put your filters inside this housing, probably a door on the bottom or something, and you can set your different filters in. So you can switch it, to the different wavelengths of light that you want to use. And this is just some specs on that hand scope. It has 7 filter wheels in it. And you get different goggles, yellow, orange, red, clear goggles, etc. And so, again, it runs on 110 volts or 220 volts. It's got an AC power supply and a rechargeable battery, which you can use for 45 minutes. That's not a lot of time. So, again, these power-hungry lights, they're great. They're super bright, but, if you can get by with an LED flashlight, then that's fantastic. But it just depends upon your situation. Okay, these are the crime lights. These are the forensic light sources. They're pretty big. This shows a small one. The one we have upstairs, they have a big battery inside that's about that big around. They're not as small and compact. You wouldn't be able to carry this thing around in your shirt pocket. But this is nice. You don't need a bandpass filter for an LED because an LED has a really sharp emission profile. So these are different lights. So you buy the violet crime light, which is very similar to what I have, but mine's actually a 365, so it's even further into the UV. It's got a very narrow source, and you can buy a blue one, a green one, a blue-green, and you have a lot of different wavelengths that you can select. And you can get into it and actually say, what kind of evidence are you looking for? You may find that it's tuned to protein versus DNA. The LED advantages, they last longer, and they're more energy efficient. You can drop them. You drop that halogen light, and it's all over. Because that little filament inside can break. Now, what's the halogen part of these halogen lamps? Like your automobile lamps are halogens. They used to have floor lamps in people's homes that were halogen lamps. They were tungsten halogen lamps. All that is it's chlorine gas, or sometimes chlorine with some xenon gas in there, that they raise the pressure inside the light bulb. Light bulbs used to have a vacuum inside. But the problem with the vacuum is that the metal, there's a little, electrons are trying to go through this filament at pretty high current, and electrons repel electrons. And the resistance of the filament is kind of like a traffic jam for the electrons. So that's why it heats up. Just like our traffic jams heat up. People's anger rises, right? And so what do the electrons do? They go around if they can. And so sometimes the electrons will leave the surface of the filament just a little bit, and you'll have a tiny amount of corona or electron gas going around the filament. Okay? And sometimes that can ionize the metals, and when the electrons slam back onto the ionized metal, it's enough for that metal to come off the surface. And if there's no gas there, that metal just leaves the surface and goes to the surface of the glass, the internal surface of the glass. And so you've seen really old light bulbs that have a bit of metal on the inside of the glass. That's what's happening. The heat from the filament is actually evaporating the metal a little bit. Okay? Now, the brighter the light, the hotter the filament. And it's difficult to get that filament really hot without more metal evaporating. So how can we get the filament hot but keep the metal stationary? We add a pressurized container. And so they put chlorine and xenon in there as a gas to hold that metal back. The metal may evaporate, hit another molecule, and go back to the filament. And so that keeps the filament to last longer. It also raises the temperature of the whole bowl, because now you can have heat transferred through that gas to the glass of the bulb. And that's why you can't touch your automobile light bulbs, because the oil from your fingers will get on the glass and provide a weak spot, a cold spot. So the glass heats up, but your fingerprint keeps one part of it cold, the other part really hot, and the shear forces will break the bulb. So that's why you're supposed to use gloves when you install these bulbs and so on. But the main point is the halogen part of a tungsten halogen lamp is inside the bulb. And all it's really doing is just increasing the temperature of the filament so you get more visible light. It's not really doing, you're not getting the emission spectrum of chlorine or anything like that. It's just the temperature effect. Now the xenon, you're getting a little bit of light from the xenon atoms being ionized, and that's why the xenon headlamps have a lot more blue in them. I don't like them because I'm sensitive to the blue. To me, that makes me want to squint. If that's your situation, then get yourself some yellow glasses. And if you're driving at night and the blue lights are making you squint, you put the yellow glasses on, and it blocks that irritating blue wavelength, and you won't have to squint. I mean, you don't want to stare right into the light bulb, but the point is you can still look at your lane and this blue light shining in your face, but the yellow blocking those deep blue wavelengths, and your body doesn't respond by making you squint. So you can keep your eyes wide open and look at your lane. So if I'm ever tired and driving at night, I've got some of these in my glove box, just some yellow safety glasses. They look so cool. So then, another advantage is of LEDs, they're not fragile. I think that's probably the number one thing. Now, we have laser light sources. Here's a couple of them. Spectral Physics is a large volume laser manufacturing company. This one's been ruggedized for crime scene use. You can see it's on this little platform. There's a box that goes over, snaps together to protect all of the fragile components. But it's on this fiber optic wheel, so you can drag this around a crime scene and illuminate what you need to illuminate, and then you can go back and wind the fiber optic back up. Fiber optics are fairly sensitive. We kink them because the light's bouncing inside the fiber optic, so it has to have somewhat of a gradual curvature. If you kink it 90 degrees and break the glass, then the laser light will leak out wherever there's a break, and it won't be transmitted to the end. So that's all I have for that. We can build that same.